So a couple things we looked at last time, the thermistor schematic, for instance, and really that's just if you're looking at how your board is connected together. And the big thing here is you have a negative temperature coefficient thermistor, and it's attached to ground. And so you could easily have a board and it's on the top side and R1's on the bottom side. You just have to know that when you're saying, okay, when I'm reading something on the analog to digital converter, um, which way is it? So as it gets warmer, this is going to go down. So, you're going to see that. So if it's on the other side, then it'll go down on the top and your voltage will rise. So which way is it hooked up? Our um, link to our Google sheet that calculates all that will ask that kind of thing. And so NTC thermistors and U was the link I was mentioning. That seems to at least be coming up right now. And create your own copy. Make a copy. And so, yeah, much nicer than yesterday. Okay, and so it has some information for you to use over here. And so it says, over. So beta value to use. And when we look at the sheet over here, the actual one that you have is the M52D1043950. So it's named that way. So that's, of course, the type of coding on it, 10 and 40. So there's our 100K and 3950 is our beta. And so if I go over here and we put in our 3950, and then it says nominal resistance, and it says 10K, but you have 100K. So you need to put 100K, and then that's going to be the nominal temperature at 25. So that's all good. And then it says, here's where it says, is your thermistor attached to VCC or ground? Well, we looked at that schematic. Yours is attached to ground. Okay, so you just need to make sure that that's moved over. And then ADC max value, you have a 12-bit ADC, which means it goes from 0 to 4095, not 0 to 1023. So your answer for that is 4095. Other resistor, your other resistor, if you look on the little board, you'll see a 103 on it. So you have a 10K is the other resistor on that little board. And so it goes off to say suggested other resistor and all that. So we can just get rid of that and put 10,000. Okay. And then, so with that, it should give way down here. It's quite neat in that it gives you this. And if you look here, it says, hey, here's your wiring, VCC to a 10K. There's the analog pin coming off. There's a thermistor and there's ground. So that's how we have ours wired. So it changes depending on whether you say VCC or ground. They're actually manipulating the data in there. And so we just right click it and we go copy. And then when I am over in my, let's go into ADC poll or source. And so if I go all the way down here, now I've cut and pasted it in. Now one of the interesting things about it, I'll just do it here just above it as well, and we'll just get rid of it in a sec. So we go and paste it in. And it even says, hey, after pasting your code in, there might be a quote mark here, which messed all this up because it's, it's looking for the other quote, thinking all of these are in quotes, and says just delete it. So you can just delete it, and then it put it all in place. So I'm just going to get rid of that one. um, because I already pasted it in. And so that's down in your user begin, user end, because I don't want to go do something else to my graphical environment and it'll wipe out anything that's not between begin and end. So I wanted to make sure it was put in there. And there's a whole bunch of comments and things, and you can either leave them in or, if you want to get rid of some of that. Really, we're just looking for this here, right? So here is our function, and it says convert analog to temperature, and then you pass it in the value, and you pass it in the value uh, and it returns a float. When you have this, this is way down below everything else. So what you want to make sure you do is up in the function prototypes, way up above main, you declare a function prototype. If you don't do that, it'll say, in this case, well, in all the cases, if you don't define something, it says it's implicitly defined, which means I couldn't find it, so I'm going to take a guess. You call a function and it returns an int. And if that's the case, things will be happy. In this case, we're returning a float, but it thinks that you're returning an int and it will provide a pigeonhole for the data to be returned back. So you could get erroneous results. The implicitly defined says you should go fix that somehow. And in this case, it's just copying this whole thing here and sticking it way up top. And so you go up to your, so in here, I have private function prototypes, and we just copied exactly what was in there. And so now that little implicitly defined should go away. Now you might have another one because actually the function uses some logs, and logs isn't part of the standard stuff. So you might have seen an error scroll by when you go and compile in the bottom. And basically it's saying, it highlights where and says implicitly defined around the log function. And to get around that, you just need to include the math.h library, and then it'll all be happy. If you're printing, it wants stdio, standard IO, as well. The other thing I've had people ask with this is, let's see if I can find it here. I have one. Maybe it's in the other one. Let's say I wanted to define a type. I'll go put it up here. Let's go uint 32 t my count equals 0, for instance. So uint 32t. And if I highlight uint 32t, it says it's a type def of underscore underscore uint 32t. And I was talking to some people in the past, and one of the things I can do with any of this kind of stuff is I can highlight it and go open. And if you go open declaration, it'll go try and find where this is. And it's in standard int, okay? And they've come up with hopefully a nicer naming convention than we have with char and with int than you've been used to when you do the Arduino. And one of the problems is if I say int depends on how many bytes it takes up, depends on the platform it's on. For instance, if you have in the Arduino world with the 8-bit Arduinos, an int is 16-bit. When you go over to the ARM world, an int is 32-bit. So if I wrote had some functions that I used in the ARM code, and I was moving it over to an Arduino, and I had a count that I was expecting to be bigger than 2 bytes long, I might get unpredictable results. The other thing is sometimes you say a char, okay, is that unsigned or is that signed? Well, it really depends on whose compiler it is. On the PIC compiler, by default, I believe it was signed, and on some it's unsigned. So if I'm expecting to have the whole 0 to 255, and I only have half that because it assumed it was signed, then I'm getting hard to find errors because it worked. I'm assuming it was one thing and it's another. And so what they did was they said, you know, it would be better if maybe we specifically declared that kind of thing. And so you have this in standard int, you have either signed, so here's an int 64 underscore t, and so it's 64-bit and it's signed, or you have a uint, and so for instance, my uint 32t is an unsigned int and it's 32 bits long. So if I use that across different platforms, a uint32t is unsigned and it's 32 bits across the platforms. Okay, so there's these hard to get little errors. It worked, but I didn't realize that an int was 2 bytes in your system instead of 4 bytes. It's 4 bytes on the PC, it's 4 bytes on the ARM, it's 2 bytes on the Arduino. And so it's trying to get rid of some of those hard to find little bugs. Okay, so anytime you see it, and if you go right down to where things are, it says this is you know, an unsigned short int, or this is an unsigned long int, or you know, that kind of thing. It will go back to one of the base types, but it's to try and avoid any of these confusions. Okay. Now let's go to. I had when you go and define the that you want to use an ADC, it puts in automatically, it puts in this handle called HADC3. So it's the handler for ADC3. If I picked it on one, it generates the code. Now in the HAL document, it has a whole thing on how to initialize the ADC, which it did for you. Before it could generate the code, you actually had to go and do all of that. It stuck it in there for you. Just like when we did the GPIOs and made them outputs, it set up the structures called HAL GPIO and it did all of that for you. So all of this is there, but it doesn't know what you want to do with it, just that you wanted ADC3 and you needed it initialized. So it has this handle. And then if I look at what we did in class, really we needed to do 3 things, it said, when we looked at the HAL API. You needed to do HAL start. And, you know, if I go, for instance, HAL ADC, I'll go underscore, let's go start, and we do that, and I've got a bunch of options, and my options are HAL start DMA, HAL start IT. Now, next week we're going to look at the interrupts, so using ADCs and play with interrupts, and then we're going to do the same thing again, but using DMA. And so we'll talk about all of those as it goes along. And there's also stops for the various ones. So if I did a start, I do a stop. If I did a start DMA, I do a stop DMA if I needed to stop it. Now we're just in a while one loop and we're always going to be reading, so I don't need to stop it. One of the things about start is it's start and do a conversion. Okay, and so I saw some people when they put start above while one, that makes sense. You're just starting it. I don't need to start it more than once, but it's kind of loop. It's got both of the things in it together. The pick is like that as well. You have an on go bit, and so it will go and do that conversion. So for this case, I need to keep starting it. Now we will in future ones go just turn it on, and then I'm going to have everything happen in the background. So I may not need that in the while one loop. But we're doing a single conversion here, and there's all sorts of different options. I'll show you where they are. Talk a little bit about some of them. But we're just doing a very simple thing. There's 3 ADCs on your board, and analog to digital converters are capable of just a ton of different options. You can configure them to do multiple channels, scan between them, all sorts of things. But one of the things here, if I did start, so I'm going to go and press Control space again, and we'll go start, and it gives you it says here's handle type def. And so it's showing you, notice how it shows me, it says that the thing I'm looking for here is called HADC, and it's going to be a pointer to that. And here is, shows it, and underneath it says, hey, the only thing I could find was an instance of HADC3 for that handle. Okay, and it's passing the address of it, so it calls it, and then it's able to link into that structure. Okay, and so we have that. Now, if I had ADC3 going and ADC2 going and ADC1 going, it would pop up and go, you have 3 ADCs here, which one do you want to use? And then I have to pick, the right one. And up top, it would say there's a type def for H80C3, H80C2, H81. So it's trying to help me here. And so I just go and say, yeah, I want that one. Okay, so it did that all for us. I'm just going to delete that there because I've already got it. And then I saw, hey, there's a poll for conversion. And so now in the pick world where we just had the flag, the function just kind of looked at the flag. You had to wrap that in a while one and just wait for the flag, I think, to be set. So you waited until that, or maybe it was till cleared. I think it was cleared. And so you just sit for a while one for the flag to be no longer set, and then you jump on. It means the conversion was done. So, and I've seen a few go and say, hey, let's have a look at this. If I highlight it and I click in, well, I should be able to scroll through and look at this. And it says poll for regular conversion, the ADC conversion flags and end of conversion flags. This function cannot be used in a particular setup. It can't be used in DMA mode. It can't really be used when you set up different interrupt parameters. I'm polling for conversion. So when we set up an interrupt, I don't want to sit there and wait for it. I want to go do other things. And an interrupt kind of gives me a kick in the pants and says, go look, we're done. And then when the interrupt fires, we'll go to an interrupt service procedure and we'll go and look at it. Okay, and we'll do that in next week's. DMA says, hey, get this other piece of silicone, and when the things are done, the other piece of silicone, go grab the data and move it somewhere. So my code doesn't have to be aware of it at all. So we're going to do that in a couple of weeks as well. Okay, and so it actually has the ability in this poll for conversion to see if you've set those things up so it won't run if you've configured it for it shouldn't be polling. Okay, and so it does that. And then one of the things it has down here is there's a timeout in milliseconds, and that's kind of nice. It's saying call this, and if for some reason the conversion never finished or it didn't happen or there was some sort of error, don't hang up your code there forever, time out and go on. Okay, so that's a really nice feature to have. I'm not locked up because something didn't complete. But one of the things I would like to be able to do is I would like to be able to see what happened. Now, I didn't expect you to do this for this lab or anything, but I could get the return from poll for conversion and see that everything was okay. Okay, you could do that. And so what this will do, just as poll for conversion, is it will go and wait till a conversion is complete and then come back. Now, it could get something else. It could get either a timeout, because we said that there's a timeout, or an error. Now, I've just assumed it's going to work, and then we do something else with it. And that's fine for most cases. But to cover all your bases, what you could do is get the return value and say, hey, this is this HAL status, and say, hey, at the end of conversion, was it okay? And then only do a conversion if it was okay. And if it was an error for some reason, you could light an error light or something like that. So you could do that. And if I go this HAL poll for conversion, let me just highlight it. Oops, if I can do that, we'll go there and we'll go once again, open declaration. And so here's poll for conversion. And so that's when I highlighted it. That's when I was scrolling down through what it went and did. And so this first part of it is checks for the verification that you actually should be polling. So it sets a whole bunch of bits. And if you didn't set it up properly, in other words, I had an interrupt or DMA, and then you tried to poll for conversion, it would actually come back, but it would set the HAL status as a HAL error. Okay. And then if I continued on with this, so it wasn't that, then it sets a timer. And it sets this a tick start, and it gets a tick, and it goes through. And if it doesn't get the end of conversion, the conversion didn't complete before the timeout, and typically I like to use in that like 200. If you're not back in 200 milliseconds, give up, go on. Okay, and so it's sitting, it's going to do it way faster than that, but it's sitting in here And if it times out, then it'll return HAL timeout. Okay. Otherwise, it's going to return, where are we here? HAL timeout. Otherwise, it's going to return HAL OK. Okay. Now we didn't use it over in here on, and actually, let me just, where did it get HAL OK, HAL timeout, HAL error? Where did that stuff come from? If I highlight the return, it's a HAL status type def. Okay, and I could right click and I could go open declaration, and it's an enumerated type. HAL OK is just 0. We often return 0 when things are okay. You have a HAL error, a HAL busy, a HAL timeout, and so those are the things I might get back. And then once again, we didn't use it. It calls this function, but I'm going, okay, we're not waiting for a while one or a while this is. When it returns 0, we're good. Okay. Otherwise, I could return those different errors, and you could do something with it. So I could say only if it's on 0 do I want to go get the value, because now it's a legitimate value or something like that. But typically, that's what's going to happen, and you're going to see that. And that's all I expected for that. But if I've seen a few in the lab wrap it in that, and it's like, okay, it's different from just a standard flag. It's a whole function, and it checks all sorts of things, and it sets the timer for the timeout and all of that kind of thing. Okay. And so we get the value, and then you have to print it and again pass in. Now, one of the things that we've done here is we've just grabbed one value, and depending, you may see that your temperature jumps around a little bit. And with Wayne, did you ever do a sliding window and gather multiple values and then average them or anything like that? Or did you do that in 130? I think I may have had you all do it in the 130 class where you read in 8 values and you average them and you divide it. Something it smooths stuff out, right? Because when I read one value, even off a pot, the next time I read it, it's a little bit here or there. And then if I was printing stuff on a screen, you'd see this number jumping around, and it's like, well, that's kind of unnerving. So you tend to gather more and then divide by the number that you read in to get an average. And one of the ways, it's called a sliding window, is, let's say I had eight pigeonholes. So I go like this. Well, let's do 4 pigeonholes. I put one in here, and then I put one in here, I put one in here, I put one in here, and then I circle around, and I just keep loading this up, and then every time read the last, in this case 4, divide by 4. And so as you're moving along, it averaged the last ones. So you could do 4, you could do 8, 16, you could do 100, and it will always just take the last 100 and divide by 100. And then so it smooths out the increase and decrease, for instance, in temperatures or what have you, and makes it a little nicer when we go and print things on the screen. Okay, I'll put that there. And so hopefully everybody then also got the printf to work. And again, where we had, when I go into debug, just so I can get into debug. Which one am I in? I'm in poll. One of the things about the debugger, the G debugger, I mentioned it last time, is that we have a nice graphical interface to the new debugger. You can fire it up in command line and just type in commands and get register status and cycle through breakpoints and all. It's a little bit of a challenge to do that all on the command line, but it gives you the ability to do that. It also has the server end of things. I could actually have my device connected to another machine and remotely go in and debug. It gives you the actual server will let you have multiple versions here, although on the one device on a local machine, that can get kind of confusing, and you might find where it's saying there's a GDB link error or something like that, and it's plugged in, and it just kind of gets confused. If you had stopped this, like right here, it stopped on HAL init, and then I go back. Oh, so this is my debug perspective. If I go back up to my C++ perspective, I could start to debug again, and it would have one instance of that sitting at HAL init, another instance kind of halfway down, and it can get kind of confused. And so if you see multiple things down here, you can highlight this and go, okay, let's terminate and remove, or terminate and disconnect all. I like terminate and remove, and then remove all selected till this clears up, hopefully. And then if there's more still there, you highlight the top blue part and go keep terminate and remove till you clear all that out, and hopefully it'll let you do everything again. Okay. And so I'll go back in. Other thing I like to watch for is down here, if it is giving me talking about the same thing that was working on. So if I'm ADC poll, if down there it says GPIO, it's debugging what you're not using. And oftentimes when I go to somebody's machine too, or if I'm not sure, when it's in the C++ perspective, I will right click and delete all the tabs, and then go back into source and open up the things in the project I want to make sure it's mine. One of the key things that something is amiss between this as well is if I start debugging and it opened up another version of main, because I am in a main that I think it's working on, and if you're debugging, it opens another version of main. You're not working on what it thinks you're working on. So the one it opened up is the one it's trying to debug. So if your code's in the other one, something gets messed up. And the kind of the best sort of way, you close all the debugging features down, and then clean your project. And so you can, in the C++ window, you can go clean, and let me do it. So if I go back over, let's say it was ADC int, let's open there, and again, I don't know which one I'm working on. So, I mean, I could do that. I'm going to go close all. And then I'm just going to, so I should be working on this one. If I debug and another one opened up or something like that, you can go clean project, and it will. Okay, so in that one, it kind of did it. It could come up and say, hey, I have multiple. Do you want me to clean all the projects, which is by default often selected, or you just unselect it and just say, clean the one that I'm working on, and then rebuild it. Hopefully that fixes all the way where the IDE is pointing to the wrong projects. Yep.
Could you also close all the projects that you're not working on as well?
Yeah, you bet. Yeah.
That's not an option when you right click it there.
Yeah. So you can make sure everything is close all unrelated projects other than the one I'm working on, and make sure that they're not pointing to. The key thing is, if you try to debug and another main pops up, it's not what you're working on, and something you got to stop and try and make that go away somehow. Clean, close projects, do all of that till this all works for sure. Okay, so we're back in. Okay, and then again, we went over in debugger, and one of the things that we had to make sure everything worked, if I want, is enable serial wire viewer, and this has to be whatever your core clock is, and it depends where the project came from or what board you're working on. It doesn't have to be 168 megahertz. We fired up our clocks to be the maximum that we could on this. If you change that, lower the power, or you use another board, it's whatever the system core clock is that you have to be set up for on there. And it doesn't, by saying enable serial wire viewer, it will allow you to click the edit on the debug window, but it just doesn't work. It doesn't tell you, it doesn't give you an error, it just will refuse to do anything. Okay. And so if you didn't click serial wire viewer and enable that, then when I go to look at my data console or my data trace, this wouldn't even let me click it. So that's telling you that you didn't enable serial wire view. If you enable serial wire view, but the clocks are wrong, it'll still let you do this, but if this isn't matching up. And again, this for the data trace, it allows me just nicely to be able to just say, hey, enable something. And the key thing with this is it's got to be something that is global. It will give you, often you'll just see it's out of scope if you tried to do something that wasn't. One of the other things about any of that is if I did something with a variable, let's say I was doing this and I don't know, ADC sum. And so in my code, I did ADC sum is plus equals, I don't know, Hal get ADC or something, whatever it is, Hal get ADC, whatever that function is. Okay, so every time I go through, I add it up, and then right here, I go ADC sum divide equal, I don't know, we did 4 in this case, because I'm getting the average. Okay, so in this part of the system, I used ADC sum up here somewhere. I'll go ADC sum equals 0. Okay, so it started off at 0, and every time I read my ADC, I add 1 to it, and then maybe it's in a for loop to do the 4, and then I'll divide it by the 4. Okay, and so at certain times through the code, ADC was 0. It's changing every time in that for loop, and then it divides it by 4. So what can happen is if I chart this, depends on, this is grabbing data at kind of random times as you're running your code. So it could grab it here, it could grab it in the middle of this, and it could grab it here. So that value may be all over the place because it depends on where it saw it when it pushed the data out that debug channel. When you do the printf, well, I'll do the printf here. You're going to see it after I finished up doing things. That's when it prints out. When you do something like this, it says, hey, show me that variable as you're running. So it grabs snapshots of the variable, and that can change. Okay, so one of the things, if you see that, and where one of the options that you can get is there's in our window, you can also go show view serial wire viewer, and there's a graphs. So I can graph it. And you might see this nice variable, and then you'll see a spike where it grabbed it at a different place. It grabbed it here, or it grabbed it, before it divided by 4, like at the end of that or something. And so you can go, what's going on? Well, if you were to use that, you might have something called ADC result, up top equals 0, and where you wanted this to be at one place only, I go ADC result equals ADC sum. So the thing that you are grabbing an image of and sticking out the debug channel only updates that one time when you want to see it. Like I say, if you use just the print, it's just wherever you're going to print it. But if you use the grab the data and stick it out, it depends on what you ask for, because it will just go through the back channels and update it as it goes along through the code. You're going to see that in 2 labs. I'm sure some of you will get a nice graph. It's not this graph we're going to use. This is a nice graph. This timeline graph. They have been updating some of the debug stuff. You're going to look at some of the others, but I have found this one to be most apparent because it's just in the background as your code's running, updating some of the variables. So it'll grab snapshots of it wherever. Okay. All right, let's have a look. Uh, where? Oh, it's okay. So what we were doing, this is in the data sheet, the actual like 200-page data sheet. I like going back and referring to that sometimes. And so this is our block diagram. So we were looking at the ADC. So this is your Cortex CPU, and it's an M4, so it has a floating point in hardware, which is really nice. And the JTAG and software debugging end, that's the piece of silicon that's going out there. And it goes through this advanced high-speed bus, and then it goes to advanced high-speed bus 1, which is 168 megahertz, and it goes out through, you can talk to the GPIO ports, and then we're going down a little bit. And so this goes to the high-speed bus goes over to the advanced peripheral bus 2. And on the advanced peripheral bus 2 is, we used ADC 3, right? So there's ADC 3. So the data goes from way up here from the ARM chip, and it goes to the advanced high-speed bus and then to the advanced peripheral bus 2, which this one goes to 168 megahertz. This one's at 84 megahertz. And then we read ADC3. And so it says here's the analog inputs for ADC3. And it's got a common kind of interface over there. We also have ADC1 and ADC2 on this. And there's also an internal temperature sensor. And the next lab, you're going to read the internal temperature sensor, and it's just attached to ADC1. And that's why I had you do ADC3 for the current one, because built into the silicon, there's an ability for you to read temperature, also battery level. Remember I said that you could put a battery on this and keep data and have a real-time clock. You can actually read your battery voltage and make sure that that is still going to keep your data safe and things. So this is where I'm reading my ADC from. I want to go to, I can get it over to the place. Where is it here?